Right now, as you're watching this, somewhere above us, there's a military jet ripping through the sky, maybe at twice the speed of sound. It's not just fast. It's carrying enough classified tech to make your latest smartphone look like a Stone Age rock. We're talking about machines that defy gravity, cheat radar, and deliver payloads with pinpoint accuracy, all while pushing the boundaries of physics and engineering. In the next few minutes, we're going to pull back the curtain on the parts governments rarely show off during those flashy parade flybys. We'll peek at the engine that burns hotter than volcanic lava, the radar that can spot a golf ball from 100 miles away, the bomb bay that snaps open and shut in less than 2 seconds, and the bizarre coating that makes a 40-ton fighter practically vanish from enemy screens. So buckle up, because we're about to go deep under the skin of these incredible flying machines. This isn't just about speed and firepower. It's about the relentless pursuit of an edge, a technological ballet performed at Mach speeds, where every single component has a story to tell, a secret to reveal. The skin they don't want you to see. When most folks picture the skin of a fighter jet, they probably imagine simple sheets of metal held together by rivets, right? Well, think again. The outer mold line of a fifth-generation fighter isn't some basic aluminum shell. It's more like a living, breathing chemistry experiment, a marvel of material science designed to deceive. Take the F-35, for instance. Its skin is a meticulously engineered baked-on sandwich of 3 distinct layers, each playing a crucial role in its stealth capabilities. The foundation is a robust carbon fiber composite, but it's not just any carbon fiber. This stuff is doped with microscopic iron balls, strategically embedded to disrupt and absorb incoming radar waves. On top of that, there's a middle sheet of specialized radar-absorbent foam, designed to further dissipate any remaining energy. And finally, a top-secret clear coat that isn't uniformly thick. Its depth varies in places, sometimes thinner than a red blood cell. This isn't just paint. It's an active component of the aircraft's stealth. While the exact composition is highly classified, we know it contains ferrite particles. These tiny particles are masters of conversion, transforming radar energy into harmless heat, preventing it from reflecting back to the source. It's why, if you were to touch the surface of an F-35 on a sunny day, it might feel surprisingly room temperature, even though it's actively eating radar waves. That's the energy conversion happening in real time, a silent, invisible battle against detection. This exquisite sensitivity means that even the smallest imperfections can compromise its invisibility. That's why maintainers, when working on these aircraft, have to wear special paper booties. One deep scratch, even a tiny one, can increase the radar cross-section by the size of a hummingbird, and that's enough for modern low-frequency radars to get a lock on it. Imagine that, a multi-million-dollar fighter, potentially compromised by a scuff. The repair process for this specialized skin is as complex as its creation. Replacing a damaged section isn't like patching a car fender. Each replacement tile costs roughly $28,000 apiece, and once fabricated, it has to be baked in an autoclave the size of a school bus, under immense pressure and heat, to ensure its structural integrity and stealth properties are perfectly restored. This isn't a line item you'll ever see highlighted in a press release, but it's a critical, ongoing expense that underscores the extreme engineering and material science that define these aircraft. The continuous development in radar-absorbent materials, RAM, is a testament to the arms race in stealth technology, constantly evolving to counter new detection methods. While older stealth aircraft like the F-117 Nighthawk relied on angular designs to scatter radar, newer generations combine advanced shaping with these sophisticated, multi-layered RAM coatings, creating a true invisibility cloak for the modern battlefield. It's a constant battle, pushing the boundaries of what materials can do. Invisible door hinges. Ever seen a promo photo of a stealth fighter? The landing gear doors, weapon bay doors, and other access panels always look so seamless, like simple rectangles flush with the fuselage. But if you think they're just basic sheet metal and hinges, you'd be missing the point entirely. Inside, the engineering is far more intricate, a testament to the obsessive pursuit of stealth. Those hinges aren't your typical pivot points. Instead, they're often serpentine, an S-shaped carbon limb that's specifically designed to scatter incoming radar waves in 5 different directions, preventing them from ever reaching a solid, radar-reflective metal part. Engineers, in their understated way, call them waveguides, but really, they're more like incredibly complex, high-tech origami door hinges. precisely crafted to deflect energy. Consider the B-2 Spirit bomber, a true icon of stealth. On that aircraft, some of those hinges are actually thicker than the door panel itself, yet they weigh less than a paperback book, thanks to advanced composite materials. It's a prime example of how every gram and every surface is optimized for low observability. Even the torque shaft, which rotates to open and close these doors, isn't just a solid piece of metal. It's often hollow and filled with radar-absorbing foam, ensuring that even as it moves, the aircraft's radar signature doesn't spike. This meticulous attention to detail is why stealth planes always seem to close their gear doors with such incredible speed. It's not just for aerodynamic efficiency. The sophisticated hinge design, with its precise wave-scattering properties, only stays optimal for a few seconds under the immense stresses of combat loads. Keeping them open too long risks warping that $250,000 assembly, which could then compromise the stealth integrity. That's why you'll see pilots slam the gear up the instant they leave the runway, minimizing any potential vulnerability. The same principles apply to other seemingly mundane access points. Even the gaps between panels are designed with sawtooth edges or filled with specialized conductive sealants to prevent radar reflections. Every seam, every junction, every moving part is a potential radar reflector, and the engineers have painstakingly worked to mitigate each one. The sheer complexity involved in making these seemingly simple mechanisms invisible to radar is mind-boggling. It requires incredible precision manufacturing, often involving robotics and advanced composites, to achieve tolerances that are tighter than what you'd find in a high-end watch. These are not just hinges. They are an integral part of the aircraft's overall stealth architecture, a silent guardian against detection, proving that sometimes the most sophisticated technology hides in plain sight. The engine that outruns fuel beneath the sleek, stealthy skin of an F-35 lies its beating heart, the F-135 engine. This isn't just an engine. It's the most powerful fighter engine ever fielded, capable of generating a staggering 43,000 pounds of thrust on a wet day, meaning with afterburner engaged. That's enough raw power to launch a small rocket, and it's what gives the F-35 its incredible vertical takeoff and landing, STOVL capabilities in some variants. But here's a stat you won't typically find in glossy brochures, one that truly highlights the extreme engineering involved. Its core turbine inlet temperature reaches an astounding 3,600 degrees Fahrenheit. To put that into perspective, that's hot enough to soften steel, a temperature that would melt most conventional metals instantly. So, how do they keep it from melting itself into a puddle of slag? The answer lies in the incredibly advanced materials and cooling techniques used for the single crystal superalloy blades inside the turbine. Each of these blades, smaller than your hand, has internal cooling channels laser drilled so fine you could thread a human hair through 7 of them side by side. These channels circulate cool air, creating a protective boundary layer that prevents the blade from reaching its melting point, even as it spins at thousands of RPMs in a superheated inferno. It's a delicate dance between extreme heat and precise cooling. What's even more fascinating is that each blade actually grows about a centimeter during a typical 6-hour sortie due to thermal expansion. But this isn't a design flaw. It's accounted for. The thermal expansion is meticulously built into the disc design, ensuring the tips never scrape the shroud, maintaining optimal efficiency and preventing catastrophic failure. When a pilot needs an extra kick, they hit the afterburner. This system injects raw fuel at an incredible 2,200 psi. Think of fire hose pressure inside a pipe no bigger than a Coke can, directly into the hot exhaust stream. The result? 0 to 1,000 miles per hour in about 12 seconds, a mind-bending acceleration that shoves the pilot back into their seat. But that kind of power comes at a cost. When the afterburner is lit, the F-135 guzzles an astonishing 22 gallons of fuel per second. Pilots often joke that the jet doesn't burn fuel. It eats money faster than a Vegas slot machine. This highlights a constant trade-off in military aviation, raw power versus fuel efficiency. When a pilot needs an extra kick, they hit the afterburner. This system injects raw fuel at an incredible 1,200 psi. Think of fire hose pressure inside a pipe no bigger than a Coke can, directly into the hot exhaust stream. The result? 0 to 1,000 miles per hour in about 12 seconds. A mind-bending acceleration that shoves the pilot back into their seat. But that kind of power comes at a cost. When the afterburner is lit, The F-135 guzzles an astonishing 22 gallons of fuel per second. Pilots often joke that the jet doesn't burn fuel. It eats money faster than a Vegas slot machine. This highlights a constant trade-off in military aviation: raw power versus fuel efficiency. The future of these engines, as hinted at in the research, involves adaptive cycle engines. These next-generation power plants are designed to flip between high-bypass turbofan mode for efficient cruising and low-bypass turbojet mode for high-speed dashes. Imagine an engine that can dynamically adjust its internal configuration to be both a fuel-sipping airliner engine and a thunderous fighter engine, all in one. This promises a 25% fuel saving, a massive advantage for range and endurance, and a significant step towards solving the eating money problem. The engineering challenges are immense, involving complex variable geometry and advanced control systems, but the potential gains in performance and operational flexibility are truly revolutionary. It's a testament to the relentless innovation driving aerospace propulsion, always striving for more power, more efficiency, and more capability. The 400,000 bolt inside every weapons pylon, clamped firmly to the underside of a fighter jet. There's a shoulder bolt that, to the untrained eye, looks like something you could pick up at Home Depot for a few bucks. But you'd be sorely mistaken. That seemingly innocuous fastener is a masterpiece of material science and precision engineering, and it commands a price tag that would make your jaw drop: $400,000. Why? Because it's not just a bolt. It's machined from a hyper-advanced titanium nickel alloy, a shape memory material with extraordinary properties. After enduring a brutal 9G jolt, the kind of force that would flatten an ordinary bolt, it flexes and then snaps back into its original alignment within 0.01 inch. This incredible resilience ensures that the missile rail, and therefore the weapon itself, remains perfectly aligned, even after the most violent maneuvers. Losing one of these on the flight line isn't just a nuisance. It triggers a chain reaction of paperwork that travels all the way to the program office in Arlington, a stark reminder of its critical value. And it's not just the bolts. Consider the foam strips that line the inside of a weapons bay door. They might look like simple weather stripping, but these aren't just for cushioning. They're impregnated with silver particles, specifically designed to dissipate static electricity. Why is this so crucial? Because a buildup of static electricity could, under the wrong circumstances, prematurely trigger the sensitive seeker head of a bomb or missile, turning a routine flight into a catastrophic incident. The price for a mere 10-foot roll of this specialized silver-infused foam, $11,000. And to add another layer of complexity, it has a shelf life of only 6 months, meaning it needs constant replacement even if it hasn't been used. These are the kinds of hidden costs and engineering marvels that are routinely buried deep in appropriation line 2670C, a corner of the military budget where journalists rarely dig, and for good reason. The details are often mind-numbingly specific and highly sensitive. These components highlight a fundamental truth about military aerospace. Every single part, no matter how small or seemingly insignificant, is designed to perform under extreme conditions, with zero margin for error. The materials science involved in developing these alloys and composites is at the cutting edge, pushing the boundaries of strength, durability, and specialized functionality. It's a world where a bolt isn't just a bolt, and foam isn't just foam. It's a world where every component is a highly engineered solution to a specific, often life-or-death problem. The cost isn't just for the materials, it's for the decades of research, the advanced manufacturing processes, the rigorous testing, and the absolute assurance that when a pilot needs it to work, it will work flawlessly every single time. It's a stark reminder that the true cost of military superiority often lies in the details that remain unseen. The radar that thinks. It's a telescope. The eyes of a modern fighter jet are nothing short of revolutionary. We're talking about active electronically scanned array, or AESA, radars like the AN/APG-81 found in the F-35. This isn't your grandfather's dish antenna spinning in the nose cone. This is a solid-state marvel containing an astonishing 1,676 individual transmit-receive modules, each no bigger than a stick of chewing gum. Imagine that. 1,676 miniature radars, all working in perfect concert. Each module is essentially a tiny, independent radar, capable of shaping and steering its own beam in microseconds without any mechanical movement. Think of it less as a single flashlight and more like 1,676 flashlights, all pointed and controlled by one incredibly powerful brain, able to focus their beams with unparalleled precision and agility. The capabilities of an AESA radar are truly transformative. In synthetic aperture radar, SAR mode for example, it can map a city block from 30 miles away with a resolution of just 1 foot. That's good enough to tell the difference between a pickup truck and a sedan, or even identify specific building features. This isn't just for navigation. It's a powerful tool for intelligence gathering and targeting, allowing pilots to build a detailed picture of the ground below, even through clouds or darkness. But its prowess isn't limited to ground mapping. Flip it to air-to-air mode, and it can simultaneously track 19 different targets while continuing to scan for even more, providing the pilot with an unparalleled understanding of the aerial battlespace. The sheer power output of these systems is classified, but open-source physics estimates the peak power to be around 20 kilowatts. To put that in perspective, that's roughly what your entire house uses in a day, delivered in a microsecond pulse. And that burst isn't just for detection. It's so potent that it can actually fry the unhardened electronics in enemy drones, or even some older missile seekers, turning them into little more than falling lawn ornaments. Pilots actually have a term for this: zapping. And yes, there's literally a switch in the cockpit labeled EW for electronic warfare, allowing them to engage this capability. This isn't just about finding targets. It's about actively disrupting and defeating enemy systems without firing a shot. Beyond raw power, AESA radars offer incredible versatility. They can perform multiple functions simultaneously, scanning for air threats, mapping the ground, and even jamming enemy radars all at the same time. This multifunctionality, combined with their low probability of intercept, LPI, meaning they're very difficult for enemies to detect, makes them incredibly effective. The data processing required to manage 1,676 modules, fuse their inputs, and present a coherent tactical picture to the pilot is immense, pushing the boundaries of onboard computing. These radars truly are the eyes and ears of the modern fighter, providing an electronic brain that gives pilots an almost omniscient view of the battlefield, making them not just sensors, but active participants in the electronic warfare domain. Oxygen at 50,000 feet. When you're flying at 50,000 feet, where the air is thin and bitterly cold, breathing isn't something you can take for granted. For pilots, cockpit oxygen systems are no longer about clunky bottles of compressed gas. Instead, modern fighters rely on highly advanced onboard oxygen generation systems, or OBOGs. This is a marvel of chemical engineering right there in the cockpit. At its heart is a molecular sieve, packed with specialized zeolite beads. These beads are incredible. They literally pull 93% pure oxygen directly from the engine's bleed air before it ever reaches the pilot. This bleed air, by the way, is no gentle breeze. At Mach 1.6, it's compressed to a scorching 110 psi and heated to 400 degrees Fahrenheit. The sieve has the monumental task of not only extracting oxygen, but also drastically dropping both the temperature and pressure without giving the pilot hypoxia, a dangerous condition caused by lack of oxygen. But the purification doesn't stop there. A gold-plated membrane then steps in to remove any remaining nitrogen. Why gold? Because gold doesn't corrode under ozone, which is naturally present in the upper atmosphere and can be generated by high-energy processes in the aircraft. This ensures the long-term reliability and purity of the oxygen supply. The entire OBOGs unit is remarkably compact, weighing in at just 9 pounds, and boasts an impressive service life of 2,000 hours. It's a critical piece of life support equipment, constantly working to keep the pilot alert and functional in an unforgiving environment. What happens if this primary system fails? No pilot is left without a backup. A small 5 cubic inch chemical cartridge stands ready. If the OBOGs goes down, this cartridge fires, igniting lithium perchlorate tablets. This chemical reaction rapidly releases 10 minutes of emergency oxygen. Think of it as a miniature firework, roughly the size of a Sharpie marker, that actively generates the life-saving gas you need to survive. It's a powerful chemical reaction, and after landing, maintainers have to treat the spent cartridge like unexploded ordnance because it's still incredibly hot. The design of OBOGs represents a significant leap from older liquid oxygen systems, offering greater reliability, reduced weight, and eliminating the need for ground-based resupply of oxygen, making the aircraft more self-sufficient and ready for extended missions. It's a constant silent guardian, ensuring that the pilot can breathe easy, no matter how high or fast they fly. The fuel that cools the jet on. A modern fighter like the F-22 Raptor, jet fuel isn't just about propulsion. It plays a critical, often overlooked secondary role. It's the primary coolant for the entire aircraft. Think about that for a second. The same stuff that makes the engines roar also keeps the highly sensitive electronics and hydraulic systems from melting down. The fuel, often chilled to a frigid 40 degrees Fahrenheit in the tanks, circulates through an intricate network of heat exchangers. It acts as a heat sink, drawing warmth away from the avionics, hydraulic fluid, and other heat-generating components. Once it's done its job of absorbing all that excess heat, the now warmed fuel then passes through a fuel-air heat exchanger, which dumps the absorbed heat overboard, before finally being fed to the engines. This pre-cooled fuel actually burns cleaner and more efficiently, giving the jet a bonus 3% thrust, a small but significant gain in performance. But this ingenious cooling system comes with a rather disgusting downside. Microscopic bugs, specifically certain types of bacteria and fungi, absolutely love warm jet fuel. They thrive in it. As they multiply, they form what maintenance crews affectionately, or perhaps not so affectionately, call shmoo, a black slimy biofilm that can clog filters as fine as 1/500 microns. This isn't just a minor inconvenience. A clogged filter can starve an engine of fuel, leading to catastrophic failure, or it can impede the flow of fuel for cooling, causing critical systems to overheat. The maintenance crews wage a constant battle against this insidious slime. They dose the fuel tanks with specialized biocide, a powerful antimicrobial agent that costs an eye-watering $100 per pint. Miss a scheduled treatment and that aggressive slime can actually eat through an aluminum rib inside the fuel tank in as little as 6 months, leading to structural damage and fuel leaks. The technical data schedules these biocide treatments every 28 days, a routine that crews have dubbed adding the expensive hot sauce. It's a vital, if costly, part of keeping these complex machines operational. This dual role of jet fuel, as both propellant and coolant, highlights the incredible integration of systems within a modern fighter. Every fluid, every component is multitasking to save weight and maximize efficiency. The constant vigilance against microbial contamination is a stark reminder that even the most advanced technology is vulnerable to the simplest of biological threats, and that maintaining peak performance requires attention to every, often hidden detail. It's a dirty, expensive job, but absolutely essential for mission success. The ejection seat that knows altitude. When things go catastrophically wrong in a fighter jet, there's one last desperate hope, the ejection seat. But modern ejection seats, like the Aces 5 used in the F-35, are far from simple spring-loaded chairs. They are hyper-intelligent, life-saving systems, packed with sensors and sophisticated computers. The Aces 5 fires a powerful 40mm rocket motor, generating 1,800 pounds of thrust, enough to give the pilot a bone-jarring 5G kick that feels like being hit by a linebacker. But here's the real kicker. A smart controller within the seat measures barometric pressure 1,000 times a second, making instantaneous calculations about altitude and speed. Based on this data, it precisely determines whether the pilot needs 1.5 or 3 seconds of rocket burn to clear the aircraft safely. This intelligence is crucial because the ejection sequence varies dramatically depending on the flight envelope. At a blistering 600 knots over 690 mph, the seat can punch the pilot through the canopy in a mere 0.3 seconds, literally blasting through the acrylic to escape the rapidly moving airframe. However, at lower speeds, say below 200 knots, the system intelligently waits an extra beat, deploying a small drogue chute first to stabilize the seat and ensure the pilot clears the tail section before the main chute deploys. This stage deployment is critical. The main parachute then opens in carefully controlled stages, preventing the opening shock from snapping a pilot's spine, a common injury in older ejection systems. The combined weight of the seat and pilot can be around 375 pounds, and the rocket motor must accelerate that mass away from a potentially tumbling, burning aircraft with incredible force and precision. After successful ejection and parachute deployment, the seat continues its life-saving mission. A beacon automatically squawks GPS coordinates on 406 MHz, broadcasting the pilot's precise location to rescue forces, even if they've landed in the middle of the vast Pacific Ocean. The entire ACES 5-seat system costs approximately $220,000, which, believe it or not, is cheaper than that specialized bolt we talked about earlier. This comparison highlights the incredible value placed on pilot safety and the engineering marvels dedicated to ensuring their survival. It's a complex, high-stakes ballet of sensors, explosives, and parachutes, all designed to give a pilot a fighting chance when everything else has gone wrong. The human engineering involved in protecting the pilot through such violent events is truly a testament to the dedication of saving lives. The code nobody owns modern military jets aren't just flying machines. They're supercomputers with wings. An F-35, for example, carries an astonishing 8 million lines of code. To put that in perspective, that's more lines of code than a Windows operating system. This vast digital brain orchestrates everything from flight controls and sensor fusion to weapons deployment and electronic warfare. But here's the interesting twist and a constant point of contention. The Pentagon doesn't actually own all of it. Lockheed Martin, the primary contractor, retains intellectual property rights to significant chunks of the flight control software and other proprietary systems. This means that every single software patch, every update, every tweak, has to go back to Fort Worth for validation and approval. It's a complex dance between national security and corporate ownership, ensuring that the aircraft remains secure and functional while also protecting proprietary technology. These updates, which are absolutely critical for maintaining operational readiness and addressing vulnerabilities, travel via a high-speed fiber optic link, often at 40 gigabits per second. However, the jet itself has a deliberate bottleneck. It can only accept data at a rate of about 200 megabytes per minute. Any faster, and the flight computer, designed with stringent cybersecurity protocols, throws a flag, interpreting the rapid influx of data as a potential cyber intrusion. This cautious approach is a necessary safeguard in an era of constant digital threats. Software version drops for these aircraft aren't just numbered. They're often named after notable military battles: Normandy, Tripoli, Belleau Wood. It's a way for pilots to connect with history, and you'll hear them proudly say things like, "I flew Belleau Wood last night," referring to the latest software suite they're operating with. The next major software drop, known as Tech Refresh 3, promises to bring even more revolutionary capabilities, including AI-enabled threat recognition. This means the jet will be able to analyze incoming threats and suggest the best countermeasure before the pilot's brain has even finished formulating a swear word. It's a leap towards true autonomous assistance, where the aircraft itself becomes an intelligent co-pilot, constantly processing and recommending actions. This reliance on software also introduces the concept of a digital twin, as mentioned in our research context. Every physical part on the aircraft could eventually have a running, virtual avatar in the cloud. This digital twin would collect data throughout the part's life, predicting failures before cracks even form, optimizing maintenance schedules, and dramatically improving reliability. While this sounds like something straight out of science fiction, remember the idea of 8 million lines of code in a fighter jet once did too. It underscores the profound shift in military aviation, where software and data are now as critical as the hardware itself, shaping the future of air combat and maintenance. The armor. Made of glue. When you think of aircraft armor, images of heavy steel plates or woven Kevlar might come to mind. While helicopters often use Kevlar for ballistic protection, fighter jets, with their relentless pursuit of speed and agility, simply can't afford the weight penalty. So how do they protect critical areas like fuel tanks and cockpit walls? They use something far more ingenious, a specialized polyurethane foam called battle hide. It's essentially Gorilla Glue on steroids, but with a precise chemical composition and density. At a mere 12 pounds per cubic foot, this foam is incredibly lightweight, yet it possesses a remarkable ability to stop a 7.62 millimeter round cold. It doesn't deflect the bullet, it catches it. The stretchy polymer literally engulfs the projectile, absorbing its kinetic energy and preventing it from penetrating further. In early testing, engineers pushed the limits, firing a .50 caliber round at it. The foam didn't just stop it, it ballooned out, dramatically slowing the slug enough that a secondary, much lighter Kevlar layer could then effectively catch and contain it. This layered approach maximizes protection while minimizing weight. But battlehide is a multi-talented material. It also doubles as a fire suppressant. If exposed to temperatures above 600 degrees Fahrenheit, it undergoes a chemical reaction, releasing carbon dioxide. This inert gas rapidly smothers flames, preventing a small fire in a fuel tank or wiring loom from turning into a catastrophic inferno. 1 inch of this extraordinary foam offers the ballistic protection equivalent of 4 inches of aluminum plate, but at half the mass. This weight saving alone is a game changer for aircraft performance. However, working with battlehide is a nightmare for ground crews. Its sticky, resilient nature means that saws gum up after just 2 cuts. Their solution? They freeze sections of the foam with liquid nitrogen, making it brittle enough to snap like crackers. It's a messy, labor-intensive process, but absolutely necessary to maintain the integrity of the aircraft's protection. This advanced foam exemplifies the innovative material science that goes into modern military aircraft, where every material is chosen not just for its primary function, but for its multifaceted capabilities, ensuring maximum protection with minimal weight. It's a silent, unseen guardian, protecting the aircraft and its pilot from threats both internal and external. The hidden antenna farm. Look at the sleek, clean silhouette of a modern stealth fighter, and you won't see a forest of antennas protruding into the airflow. That's by design. Traditional aircraft are bristling with bumps and blades, each an antenna for communication, navigation, or electronic warfare. But every protrusion is a radar reflector, a stealth killer. So on 5th-generation fighters like the F-35, all 52 antennas are meticulously blended or conformal into the leading edges, wings, and fuselage. They're not just hidden. They're integrated into the very structure of the aircraft. Some of these antennas are simple slots no wider than a credit card, seamlessly cut into the skin. Others are complex fractal shapes etched directly into the composite surfaces like intricate snowflakes, each precisely tuned for a specific frequency band. The magic really happens with the software-defined radio SDR system. This incredible piece of technology can switch between these various antennas in nanoseconds, dynamically reconfiguring itself to talk UHF to a tanker, Link 16 to Allied forces, and MADL, multifunction advanced data link to wingmen, all without ever physically moving a single part or protruding from the aircraft's skin. It's like having dozens of different radios and antennas, all operating simultaneously and seamlessly, managed by a single intelligent brain. The redundancy built into this system is equally impressive. If one antenna is damaged or fails, the jet automatically reroutes signals through surviving apertures, ensuring continuous communication and situational awareness. To ensure the integrity of these critical integrated systems, engineers perform rigorous testing. They zap sections of the aircraft with 20,000-volt static wands. If a spark leaves a pit deeper than 0.02 inches, a tolerance finer than a human hair, the entire panel, which can cost $76,000, gets swapped out. That's why maintainers are often seen meticulously inspecting the aircraft's skin with dental probes and flashlights the size of cigars. They're looking for micro damage that could compromise stealth or antenna performance. This intricate integration of electronics and structures is a hallmark of modern stealth design, proving that sometimes the most powerful technology is the one you can't even see. It's a constant battle against the laws of physics, ensuring that the aircraft can communicate effectively while remaining invisible to the enemy. The bomb that listens to Wi-Fi gone are the days when smart bombs just meant strapping a GPS kit onto an old iron bomb, creating a JDAM. The new generation of precision-guided munitions, like the GBU-53 Stormbreaker, are not just smart. They're incredibly perceptive and adaptable. This weapon carries a sophisticated tri-mode seeker, giving it an unprecedented ability to find and hit targets in almost any condition. It combines millimeter-wave radar for adverse weather and obscurance, infrared for thermal signatures and passive targeting, and semi-active laser for terminal guidance and precision. But here's where it gets truly fascinating. While flying under strict radio silence, the Stormbreaker can passively sniff out enemy radar emissions, triangulate their positions, and even autonomously retarget itself mid-flight. Imagine a college intern who can not only finish your sentences, but then also independently go grab you coffee and anticipate your next task. That's the level of autonomy we're talking about here. Field tests have demonstrated that a single F-35 can launch a salvo of 4 Stormbreakers, and each bomb can independently track up to 96 different armored vehicles, ranking them by threat algorithm and engaging the highest priority targets. This capability allows a single aircraft to neutralize an entire convoy or armored formation with a single pass, a monumental leap in combat efficiency. The price tag for this level of sophistication? Approximately $195,000 per bomb, which you might recall is actually cheaper than that special bolt we discussed earlier. This illustrates how the cost of advanced munitions, while high, is often balanced against the strategic advantage they provide. From an altitude of 40,000 feet, the flight time to target is around 7 minutes, giving the bomb ample time to analyze its environment and refine its trajectory. Impact speed clocks in at 950 feet per second, faster than a bullet fired from an AK-47, ensuring devastating kinetic energy delivery. These aren't just bombs, they're miniature autonomous hunters, revolutionizing air-to-ground warfare and making every enemy vehicle a potential target, even when operating under the cloak of radio silence. It's a testament to the future of networked intelligent weaponry, where the bomb itself makes critical targeting decisions. Section 13. The secret exhaust that fools missiles. Stealth isn't just about the front end of an aircraft. It extends all the way to the exhaust because the backside matters just as much, if not more, for avoiding detection. The F-135 engine in the F-35 uses a complex thrust vectoring nozzle equipped with chevrons, those tiny triangular saw teeth you might notice around the nozzle's rim. These aren't just for show. They actively mix cool ambient air with the scorching 1,800-degree exhaust gases, effectively dropping the infrared signature by a significant 25%. This cooling and mixing makes the jet much harder for heat-seeking missiles to lock onto. But the infrared trickery doesn't stop there. Inside the tailpipe, there's a ceramic matrix composite liner. This advanced material, even when glowing orange from the extreme heat, is designed to emit infrared wavelengths that are shifted away from the specific bands that missile seekers typically look for. It's like trying to find a specific color in a spectrum that's been subtly altered. Pilots can even engage a donut mode, which pulses cooling air 30 times a second, creating a strobe effect in the exhaust plume. This flickering, non-uniform heat signature is incredibly effective at confusing the tracking algorithms of heat-seeking missiles, making it almost impossible for them to get a stable lock. For ground crews observing with night vision goggles, they might see a faint flickering heat signature, but from 10 miles away, a MANPADS, Man-Portable Air Defense System operator sees nothing but noise, a chaotic jumble of infrared signals that don't coalesce into a clear target. This level of thermal management is incredibly challenging. Each nozzle is designed to last approximately 1/200 flight hours, but the constant exposure to extreme heat and rapid temperature changes eventually takes its toll. The advanced ceramics start delaminating, much like old drywall peeling away. When that happens, replacement isn't cheap. A new nozzle assembly can cost a staggering $2.3 million, and that's before shipping and installation. This illustrates the immense cost and complexity involved in maintaining the stealth properties of a modern fighter, where every component, even the exhaust, is a highly engineered system designed to deceive and survive. It's a silent, invisible war being fought with heat and light, ensuring the aircraft remains elusive in the face of advanced threats. The pilot's watch, that's a backup cockpit in the cockpit of a modern fighter. Every piece of equipment is critical, right down to the pilot's wrist. While it might look like a high-end consumer device, the Garmin Mark Aviator on a pilot's wrist is far more than just a fancy timepiece. It runs custom military-grade firmware, transforming it into a vital piece of backup equipment. This Jesus band, as pilots affectionately call it, as in when all else fails you still have time on your wrist, pairs via Bluetooth Low Energy directly to the jet systems. If the main cockpit displays suffer a catastrophic failure, a rare but possible event in combat, this watch can instantly display critical flight information, altitude, speed, heading, even bingo fuel levels with a flashing red alarm. It's an emergency cockpit on your wrist, providing essential data to keep the pilot oriented and aware. The durability and power management are impressive. The battery lasts an incredible 12 days in smart mode or 48 hours in continuous flight mode, ensuring it's always ready. But its life-saving capabilities extend beyond the cockpit. In the event of an ejection, The watch automatically logs the precise GPS coordinates of the pilot's landing site and pings the same rescue frequency as the ejection seat. This redundancy significantly increases the chances of a swift and successful rescue, even in the most remote and hostile environments. At $1,800 per unit, it's cheaper than the specialized foam roll we discussed earlier, highlighting the military's strategic integration of commercial off-the-shelf technology, adapted and hardened for combat. However, this blend of consumer tech and military application comes with its own quirks. Software updates for the watch arrive via a phone app. If a pilot forgets to sync their watch before takeoff, the jet, in its digital wisdom, refuses to upload navigation waypoints to the aircraft systems, effectively grounding the flight until the watch is updated. Nothing like a smartwatch acting as your supervisor, ensuring all systems are go before mission launch. It's a fascinating example of how even personal devices are being integrated into the complex, interconnected ecosystem of modern military aviation, providing critical redundancy and an extra layer of safety for those who fly into harm's way. The future under the hood, the relentless pace of innovation in military aviation means that what's cutting edge today will be standard tomorrow and obsolete the day after. The next generation of programs, NGAD, Next Generation Air Dominance in the US, Tempest in the UK, and FCAS, Future Combat Air System in Europe, are already pushing the boundaries of what's possible. A major focus is on adaptive cycle engines, which we touched on earlier. These engines are designed to literally flip between high-bypass turbofan mode for efficient cruising and low-bypass turbojet mode for high-speed dashes. This chameleon-like capability promises a staggering 25% fuel savings, dramatically increasing range and endurance without compromising speed. It's an engineering marvel that could redefine global air power projection. Materials science is also undergoing a revolution. Additive manufacturing, or 3D printing, is no longer just for prototypes. Engineers are now printing complex compressor blades with internal lattice structures, allowing for intricate designs that reduce weight by another 5% while increasing strength and heat resistance. These internal structures were previously impossible to create with traditional manufacturing methods. Meanwhile, a truly mind-bending concept is gaining traction: metamaterial skin coatings. Instead of absorbing radar energy, which still generates some heat and leaves a faint signature, these theoretical materials promise to literally bend radar waves around the aircraft, making it appear as if nothing is there at all. This could theoretically cut the radar cross-section by another order of magnitude, making detection incredibly difficult for even the most advanced radars. Beyond the airframe, directed energy weapons are rapidly moving from the realm of science fiction to reality. Laser pods, currently in ground testing, are rated at 150 kilowatts, powerful enough to engage incoming missiles or drones. These compact systems will likely ride on conformal arrays, firing up to 50 shots per recharge, offering a virtually unlimited magazine and pinpoint accuracy. Imagine a fighter jet that can vaporize threats with light. And then there's the concept of digital twin maintenance. Every single part on the aircraft, from the smallest rivet to the largest engine component, will have a running virtual avatar in the cloud. This digital twin will collect real-time data on stress, temperature, and usage, constantly predicting potential failures before cracks even begin to form. This predictive maintenance could dramatically reduce downtime, improve safety, and optimize logistics, fundamentally changing how military aircraft are maintained. If all of this sounds like something straight out of a sci-fi movie, remember that the F-35's 8 million lines of code once did too. The future of air combat isn't just about faster jets. It's about smarter, more adaptable, and more invisible machines pushing the boundaries of engineering in every conceivable direction. These are the advancements that will define sixth-generation fighters, ensuring air superiority for decades to come. CTAIF. You're as fascinated as we are by these deep dives into technology they never show on the news. Then do us a solid. Smash that subscribe button and tick the bell icon so YouTube actually shows you our next upload. And here's a challenge. Comment below with the military aircraft you want me to peel open next. If this video hits 50,000 likes, I'll storyboard whatever you pick and give you an even deeper look. Your curiosity fuels our content. Conclusion. We started this journey with a seemingly simple rivet and ended up talking about lasers and digital twins. Under the hood of a modern military jet, You'll find an incredible fusion of cutting-edge chemistry, mind-bending physics, advanced computer science, and a budget spreadsheet that could make even the most seasoned defense contractor shed a tear. Every single bolt, every specialized foam strip, and every line of code represents a meticulously calculated trade-off between raw performance, astronomical price, and the one thing militaries hoard most fiercely: information. The jets you see performing graceful aerobatics at air shows are undeniably gorgeous, but the true marvels, the real secrets, are hidden away, humming quietly, waiting for a pilot to flick a switch that most of us will never even know exists. Next time one of these incredible machines roars overhead, don't just hear the noise. Remember, that loud rush isn't just the sound of power. It's the sound of secrets passing by. A symphony of unseen technology pushing the boundaries of what humankind can achieve in the skies.